Colin earned his PhD in geography from the University of Wisconsin-Madison. He's taught courses on geomorphology, river systems, and field mapping in the Department of Geography and Environmental Science at the University of Wisconsin-La Crosse since 2009. He currently serves as the Associate Director of the UWL River Studies Center. His research includes quantifying human impacts on river systems in southwestern Wisconsin, including floodplain sedimentation and contamination. He incorporates unmanned aerial systems, GPS, and sonar to quantify landscape change. So let's welcome Dr. Belby.
See if I remember how to do this. Thanks. Can you hear it all right?
Yep.
Excellent. Well, I appreciate you all coming out on a chilly Tuesday, I guess it is, evening, to hear about river systems, and let me know if I'm blocking you at all, but to hear about river systems in the community and the region that I imagine you all live in. And I imagine many of you probably have a lot more experience being in these sorts of environments than I may even have in these environments. So at any point, as I'm going through, don't hesitate. I don't mind if there are questions or comments or things that you want to interject with as I move along. It's the same sort of thing I encourage my students to do as I'm talking, as actually 3 folks here can attest to. I got 1 former student there behind the bar and 2 back there in the corner, and I got my 2 kids over here that are eager to find something else to listen to. So I was asked to give this talk, and I was very, very happy to do so. I grew up in Rock Island, Illinois, just a few hours to the south, and I grew up on the Mississippi River. It's in many ways a different type of environment down there in the glaciated portion of the Midwest. But in many ways, there's a lot of similar impacts that exist down there as exist up here as well. And so humans have been on the landscape for thousands of years, of course. But the impacts of humans on the landscape and subsequently on river systems really kind of accelerated beginning in the mid-19th century here, particularly up in this part of the state, 1820s, 1830s, and into the 1850s, beginning with mining and then continuing on into agricultural land practices and urbanization to an extent. So the video here, though, that just played through, that is the site that I've been doing a little bit of work on just to the south. Does anybody know where that site is? Actually, I know there's 1 person in the room at least that knows where it is. Yeah. So this is Plum Creek, located near Wazeeka, tributary to the Kickapoo River. This is the Plum Creek Conservation Area that was recently acquired by the Mississippi Valley Conservancy. And it's a project that I've done, and a student I've done a little bit of work on up to this point. And part of the question is, can we potentially restore some sort of semblance of natural processes at this site? And so if we're going to do that, we have to have an understanding of what have the changes been to this site. What are the natural processes at this site? What time point do we go back into to define what the natural processes are? And we can define those things in a variety of different ways. I'm not necessarily here to give you an answer to that. I'm just going to talk a little bit about some of the different changes that have occurred, and maybe a little bit about what the landscape would have looked like in the past, because it didn't necessarily look like this, right? We look at this landscape here and we see the dense forest. Of course, there weren't cattle on it. But the topography of the floodplain here looks relatively homogeneous. That probably wasn't completely natural. The height of the floodplain surface relative to the river probably isn't completely natural. The vegetation in the floodplain is maybe not natural. Right? So there's a lot of things that have changed. But if we look at the stream is relatively clear water. Well, why is the stream clear water? Well, it's tied to the bedrock geology in large part, and it's tied to the vegetation in large part. And if we start to change some things within that landscape, we start to change what the land cover is, what the density of the vegetation is, then we start to impact the clarity of the water, the sediment load that's in the water, and the subsequent surrounding floodplain environment. But when we start to talk about our rivers and the flow of waters within the rivers, it's important to keep in mind the idea that Wisconsin today isn't where it's always been. Wisconsin, if we go back in time, these numbers aren't tens to hundreds of years ago, these are millions of years ago. And so if we go back far enough in time, Wisconsin would have been located about 15, 20 degrees south of the equator, if we go back to about 500 million years ago. And so the rocks that we're sitting on top of right now are 450 to 550 million years old, older as you go further down. If you go far enough down, you get to rocks over 1 billion years old. But I'm talking about the young stuff on top, about 500 million years old. So we're moving right now at about 2 centimeters per year, right? We're zipping along at about 2 centimeters per year towards the west, southwest right now, okay? We don't feel that obviously, but that's not always what the direction has been, right? So we're down here in a tropical latitude, kind of worked our way up here through our processes of plate tectonics and continental drift. So if you were on this landscape about 450 or so million years ago, this is where we are today, just shy of 45 degrees north. And so we would have been located down there at a more southerly latitude, turned on our side about 90 degrees and underneath water. And so the materials that would have been coming into that shallow ocean would have been deposited, and depending on the depth of the water, you would have different types of materials getting deposited. If the water's shallower, near a coastal environment, you would have had sands. If the water gets a little deeper, you maybe would have shales, or maybe you would have carbonate sediments that make up our limestones and dolostones or dolomites that we have. The karst type of materials that are highly influential. And so if you look here, of course, we are down around in this region where the star is located here, and so we have this layering of rocks that we find here. So this is from, if any of you don't have this, I highly recommend getting it, the Roadside Geology of Wisconsin. It's a fantastic resource. And it shows the layering of rocks that we have. This is a cross-section from La Crosse to the southeastern portion of the county here. And so we can see we have this layering of rocks. It's part of the reason why the ridge tops look so flat. Or if you go to the Mississippi River and you look at the ridge tops, they look relatively flat. For the most part, those rocks are pretty flat. They're dipping a little bit, but they're pretty flat. And we get this different layering of rocks, and that layering of rocks is associated with those oceans, those shallow oceans that were here that came and went a couple different times. And they have shells and other fossils embedded within them that give us a sense that we would have had this tropical environment. Okay? You might wonder why the hell are you talking about this? You're supposed to be here talking about rivers. Well, so the Driftless Area is known for its trout streams, in addition to many other things. Well, why do we have so many trout streams? Well, it's in part related to the abundance of springs that we have here. And so why do we have so many springs found within this region, including this one that's located just down the road? There's a Wisconsin Geological and Natural History Survey did a survey of springs throughout Wisconsin. You can find it online, you can find pictures of them, figure out where they're at. This is one that's nearby. So this is where we can see this layering of these rocks, and where you get different types of rock or different permeability of material. Sometimes the water, instead of going down vertically, will take up the path of least resistance and go horizontal. And if it does that for long enough, it might eventually come out at the edge of the hill slope, or even within the, in this case it says lake, but it might be a river. So we get these springs. Well, those springs then help to sustain the flow within our streams, and they help to maintain the cool, oxygenated water that is vital to many different types of life forms that we have within our water bodies. Okay? Bonus question here for folks. What do you think is associated with these springs that we see here? Why are there so many here?
The Continental Divide up there?
not the continental divide, but it is kind of a divide of something that happened and something that didn't happen. Big hint here. Yeah, so this is a moraine, right? So these are associated with moraine and the types of materials found within the moraine, glacial moraine. So if we look at where we have our trout streams, they tend to be associated with where we have our springs. And so we have an abundance of trout streams that are found here. And these trout streams, of course, have a large economic impact on the region. This was a study that was done by Trout Unlimited with assistance, I think, from researchers at UW-Well. So a major economic impact associated with those trout streams. Right? But it's tied to, in large part, the springs, which are tied to the bedrock, which is tied to something that happened here 500 million years ago. Which in my mind is always kind of mind-boggling in many different ways. And that happened in the tropics south of the equator. On a landscape that was underwater at that point, but when it was above water, it was devoid of vegetation. Okay, so the bedrock of the area is really important for helping to define that kind of layering of rock that we see there, and the position where different springs might be located. But it's also valuable for us when we talk about rivers to think about the slightly more recent history, the glacial history, or lack thereof, here in the Driftless area. So if we look at this is these are oxygen isotopes. We don't need to get into the weeds on that, but what this is essentially showing us is when we had conditions associated with glaciers advancing and glaciers retreating. And it's showing us the past 2.7 or so million years, 2.6 million years. And we came out of the Wisconsin glaciation most recently, and we're currently in what's called the Holocene interglacial. Warmer period, more vegetation on the landscape, very different than what we would have had here during the Wisconsin. If you go back a little further in time, there's the Illinoisan glaciation, and then if you go back beyond that, we just kind of lump all that together into the pre-Illinois. There were many advances and retreats that would just kind of wipe out the records of the previous ones. So we just say it's pre-Illinois. Okay? So if we look at where the glaciers have come or not gone within the region, we see that we had the Illinoisan and pre-Illinoisan coming down this far. We've had the Wisconsin most recently came here and here, so about 19,000 years ago we would have had ice kind of in these regions here. But the Driftless area has escaped glaciation. Now, oh my goodness. Did it close altogether or did it just go to the background? No. So
is this what you want?
We'll go back one. So we were not glaciated, but what I want to remind you of is that even though this area was not glaciated, the area was still highly impacted by glaciers. So glaciers were nearby. It was a very cold environment. There would have been a lot of freezing and thawing of that bedrock. That would have introduced a lot of rock fragments that worked their way down the hill slopes and got into the valley bottoms. And that rock that got into the valley bottoms serves as an armored layer on top of which our streams are migrating back and forth on top of. Okay? In addition to that, if you go to a glaciated environment like this up in Alaska today, there's a glacier just upstream from this. That would have been kind of like what the Mississippi River would have been like. We would have had a braided river, lots of sand and gravel exposed with silt, small particles that the wind would be strong enough to pick up. And that material that the wind is picking up there in the image, and ultimately it might get redeposited on the hill slopes, is it is, we might call it dust, but it's called loess. Or if you're German, you might have a slightly different way of pronouncing it than I do. So loess is wind-deposited silt, mostly silt. There could be some sand, very fine sand, and some clay in there. Okay? So again, if we look at where we are within the state, we see that we have very thick loess deposits that are found here on our hill slopes. those loess deposits are pretty fertile. They have a lot of nutrients within them that are useful to the types of vegetation you might want to grow in those soils. Okay? The problem is loess, because it's made out of silt, is also very, very easy for water to erode. So if you expose that material to rain, it will be dislodged pretty easily and it'll start to move across the landscape pretty easily. So it's fertile stuff, but it's easily eroded material. Okay, so we know a little bit about the bedrock, we know a little bit about the parent material for the soils, this stuff called loess. We know that we're in the driftless area, so it's an unglaciated landscape, so we have a lot of topography here. It wasn't flattened out by the glaciers, filled in by glaciers like in other parts of the state. And as we came out of the glacial times and got into this interglacial period, the climate, of course, warmed up, and we had various vegetation changes that occurred over time. These are documented by pollen that's found in lakes all over the region. But getting closer to present, as we get into the mid-19th century, there were land surveyors that went across and walked the landscape. And as they walked the landscape, they took notes on various things, including the vegetation that they found at section corners along the way. And so people have taken those old surveyor notes from the 1840s and 50s and reconstructed what the vegetation would have been like at kind of a coarse level for Wisconsin. And so if we look at this here, the yellows are primarily, we'll see this prairie and oak savanna, and then we have some southern oak forest and southern music forest. But we see that there would have been a lot of prairie and oak savanna or oak openings found in this area. Right? That would have been the vegetation cover that the European American settlers would have come across as they started to populate this landscape. So this is a quotation from one of the earlier European American visitors to the area, talking about the Pecatonica River. It says, in front the Pecatonica flowed past, forming a large and picturesque band bordered by a row of willows into which a good-sized creek emptied into its clear and transparent water. That's an important part of it. Clear and transparent water, which the trout could be seen swimming. On the northwest, a fine grove of oaks and elms completed the picture. Right? So it would have been a landscape that would have looked something like this based on the paintings from that era. Right? So think back to that video at the beginning where you saw that dense forest. That maybe wasn't the case at that point in time because you would have had fire that would be periodically burning across the landscape and would have helped to keep things a bit more clear. One of those early land surveyors that helped to provide that documentation used to create ultimately the vegetation of Wisconsin, David Dale Owen, he described the driftless area as prairie-covered uplands, generally wooded valleys, mostly oak, and said the water was clear as crystal, and the soils had an unusually black appearance, indicating a large proportion of decomposed vegetative matter, often 4 or 5 feet deep. So again, this idea that you would have prairie oak savanna, black top soils associated with that prairie oak savanna type of vegetation, and very, very fertile soils. These are what we call mala soils. Mala meaning soft, sol for soils. Soft soils are some of the best soils in the world. And so this is probably similar to what a cross-section of those soils would have looked like. Dense above-ground biomass and very dense below-ground biomass. And that would have helped to hold that loess in place within those soils. And it protected it from rainfall, it protected it from water moving across that surface. That vegetation built up organic matter to create that black color to it. It's very similar to that brownie that you served my kid a little bit ago. He kept saying, look how black this is. And it looks like that soil picture that I have coming up. So then, General Williams here, as he was going through the area, described this rich soil with black mold. He proclaimed that the first crop will pay more than pay all the expenses, right? Talking about just how valuable this soil is because it is so incredibly fertile. So it is primed for plowing up and planting row crops, particularly wheat initially. So, all right, I'm going to get to rivers at some point here. So again, you know, if we could take that soil in this previous picture and shake it all out and look at the vegetation, it would maybe look something like this, the tall grass prairie. Right? So think of the root mass associated with that and the job that that's going to do to help hold that soil in place, right? In addition to the protection that you get above ground from all that vegetation. And if you could, you know, if you could look at this soil here under a microscope and look at it closely, you would see that the individual particles of soil are kind of bound together, or glued together to form these larger particles with big pore spaces between them. And so those big pores help to serve as conduits for water to soak into the ground. Right? So it's like the ground is a big sponge that water can soak up into. So the vegetation slows the water down and then helps to infiltrate the water, and the pores there help to move it through. And then you got bedrock beneath that, like we just saw, that is fractured and cracked, and so it has pathways for that water to continue to move down. And eventually, it finds a way to move laterally, and it comes out at springs in another location. So under that native vegetation, if you were to dump a bunch of rain on the landscape in a short period of time, it could probably soak most of that up, if not all of it. Right? This is probably a vast underestimate. I pulled a figure out and I switched it from centimeters to inches, and actually that isn't native vegetation. The infiltration rates are even higher than that for native vegetation. But what I want you to just remember is that it's high. Right? So this is cumulative infiltration. So if you were to dump a bunch of rain on the surface, that soil could soak it up. Okay? So if you think about, if you've ever looked at which I know many of you have, a hydrograph, the idea of stream flow over time at a location. So these bars here, the idea is this is rain falling on the landscape, and then that water eventually works its way into the soil, works its way through the ground or over the ground, and comes out in the river, and there's a response in the river in terms of the amount of flow in the river. And then it passes through, and then the river drops back down, right? And so on this sort of landscape, rain falls, and you get a pretty muted response on that stream. It would go up, but it would take a bit of time to go up, and it wouldn't go up very high, and then it would slowly taper back off. And most of that water would probably go into groundwater recharge, and there would be very little surface runoff like we see on the landscape today. Right? So we call this a non-flashy response in a river, right? A non-flashy response. Versus if we come in and we plow the landscape, till the landscape, have very little of that natural vegetation cover remaining anymore, and potentially work the land in a way that doesn't take into account much the topography of those hill slopes, then we create a situation where we greatly increase the potential for the water to now run across the top of the ground rather than soaking into the soils. And so this old timer here, it looks like it's plowing up and down the slope, which is not really advised at this point. And that tilled soil is going to have, because you've removed the vegetation cover and you've exposed bare ground, it's potentially not going to infiltrate nearly as much water. So if you dump the same amount of water on the land as we saw on the previous slide, the response is going to be much, much different on this type of landscape. The river is going to rise faster, it's going to reach a higher peak, and then it's going to drop off and reach a lower low. And the groundwater contribution is going to be much less to that stream because the water has routed through much faster as surface water. Okay? So that is what we've transitioned to with our rivers, particularly starting in the around 1840s, 1850s here in the Driftless area. And a lot of it's tied to this idea of land clearance for agriculture. So if we take a field, this doesn't happen. My brother built a new house a few years ago. The same damn thing happened in his property too. I'm not picking on agriculture or anything here, but this is the reality of it in this part of the state though. So, you know, if you take the field and you have a point during the year where you have bare soils, and if we go far enough back in time, things wouldn't be planted as closely together either. Then you have that potential for water, for rain, to hit that ground. We think, wow, rain doesn't. What's rain going to do? Go outside, right? Look at the side of your house after it rains in the spring, and you see all the mud splashed up on the side of your house or on the side of your car. It's the same idea here. So the rain is dislodging those soil particles. Once it's dislodged, you now have water moving across the top of the surface that picks up that dislodged particle and starts to transport it away. That water doesn't tend to stay in a thin sheet across the surface. It typically starts to flow in rills and gullies. It becomes concentrated, and the potential for erosion is even greater at that point. So even more material is being transported away. So raindrop impact, really, really an important process that, if you're working that land, you probably have a sense that you need to keep crop residue on that surface in order to protect the soil. So how much erosion comes? How much sediment transport are we actually talking about from this sort of process? Well, there are ways to figure this out. There's a variety of different tools. There's modeling, there's actual field sampling that can happen. This is a project that was done, so I went to UW-Madison. My PhD advisor was Jim Knox, prolific researcher and native of the Driftless Area. And so he went to a site in central southwest Wisconsin where there was a field that had been cultivated for about 150 years, and adjacent to that, it was a railroad right-of-way that had been prairie the entire time and never tilled up. And so he took sediment cores from both of those adjacent fields. Now remember, the soil that is there is an artifact in part of the loess that was blown in on that landscape. Well, sometimes the wind was blowing strong, so the loess was a bit coarser, bigger particles. Sometimes the wind was a little weaker, so it was a little smaller particles. Right, so there's variability in terms of the size of the materials. So if you were to core down through there, you can actually look at the variability. In this case, it's percent clay here. Try not to throw too many graphs at you. Clay, and this is carbon. And so if we look at this, these adjacent soils, one, you can see this black extends further down for the prairie soil. It doesn't go as far here. So the question is, well, how much erosion has occurred in that cultivated field that is in a relatively flat area? And so what you can do is you figure out how much clay is in both of these from the top going all the way down. And then, my shadow's blocking, you can slide one of the graphs up and down to figure out where it lays over the top of the other, where they fit each other. And so the amount that you have to slide it down is telling you the amount of material that has been eroded off the top of one of those sites. You follow me on that? And so if you do this, it comes out to 38 centimeters. So 38 centimeters, we're talking a foot and a half or so of material that has been eroded. The farmer apparently was astounded by this because the farmer didn't really think that there was much erosion occurring on that property, on that relatively flat upland site. Right, so that is a large amount of material that's being eroded off that hill slope. Well, so we have increased surface runoff because of decreased infiltration, increased erosion because of decreased infiltration and increased runoff. And we have increased runoff. Well, that water's got to go somewhere, so we have higher surface runoff. And that water gets routed into those rills and then the gullies, and it quickly gets into our streams, and it quickly gets into our larger river systems. And so folks have modeled what the change has been on these river systems in terms of the size of floods of certain frequencies. In this case, it's what we call the 10-year flood, the flood that on average would occur or be exceeded once every 10 years. And so for the 10-year flood, it was estimated that the changes in land use and land cover resulted in a 5- to 6-fold increase in the magnitude of the 10-year flood, which is a relatively frequent flood. And so as a result, cities like Chaseburg and Coon Valley, and many other places that are found in the valley bottoms, were inundated much, much more frequently, seemingly every single year. The occurrence of these floods was higher.
More frequent or higher?
The magnitude, I should say, was getting say hi. I interchange these words, and I shouldn't sometimes. The magnitude is getting greater in the floods of a given recurrence interval. We're getting larger. So that's saying the same thing twice.
Right.
So if we say a given discharge, the frequency of a given discharge is becoming more frequent, or the magnitude of a given recurrence interval was getting larger.
Both?
That makes sense?
So you're saying both?
Yes.
Got
Yes. Yeah. More frequent flooding and bigger floods. There's a better way of saying that, huh? So, yeah, right. So, all right, so what's the impact of that going to be then? If we start to have floods happening more often and the flows being larger, what's that going to be? Well, our streams are sized to a certain discharge that happens on a certain regularity. Well, if we increase the frequency of larger discharges, then our streams should start to get bigger. Those larger flows are more energetic and they have the ability to start to erode material. Well, remember I said, hey, I kind of glossed over it, but I said, hey, there's this gravel layer that's found in our valley bottoms, and that's in part tied to the erosion of the bedrock during glacial times and the downslope transport into the valley bottoms. So that helped to form this gravel layer. So oftentimes when you see rivers, when they have excess energy and they're hungry, they try to pick up sediment, frequently they will cut down. In this case, the ability to cut down was limited to an extent by that gravel layer. It takes a lot of energy to move those bigger pieces of material. And so rather than cutting, more of that energy, at least in this area, if we go further north it's different, was expended on lateral migration. So the rivers started to laterally migrate at a faster rate. In addition to that, the cross-section area of those channels increased, which meant the capacity of the channel to hold that water increased as well. But that takes time. It will happen pretty quick, but it does take time. And so if the cross-section capacity is not large enough to hold that water, the water's got to go somewhere, so it spills out onto the floodplain. And that's generally considered a good process, or a good thing. If we're talking about floodplain, there's a lot of nutrient cycling and other beneficial things that happen when water spills out onto the floodplain. But when you have the sediment loads of these rivers that we were talking about due to the massive amounts of erosion that were occurring on the hill slopes and in the gullies, then we start to deposit large quantities of sediment out into the floodplain. So we see that the natural pre-European American settlement size of the river there, it gets larger as we get bigger flows coming in, but we also see the aggregation, the building up of sediment out onto the floodplain. And so the river is becoming disconnected from its floodplain as a result. A lot of arrows there. I think I covered all those things. Increased shear stress. Yeah. Okay. Does that idea make sense?
Yeah.
Okay. So, when we have these large floods occur, and this could be a picture from a couple of years ago. Unfortunately, we're seeing big flows again. But again, this idea of larger floods have the energy to transport a lot of material. Some of it's big material that it transports, some of it's a smaller material. But they reshape their channel cross-section and in the process of that water moving through them. Now, it's pretty tough to see in this image, and you'll see it better in the next image, but we can actually get a sense of how much material, in this previous one I said material is building up on the floodplain over time as that water spilling out of the channel out onto the adjacent relatively flat land. Well, how do we know how much has built up? Well, if you kind of squint your eyes enough, you might see there's that dark layer there, and there's a dark band here, and this says, hey, this is above that band is agricultural post-1820 sediment from this area a little further to the south where mining started earlier. And then here saying, hey, Holocene, I mentioned that term, right? We're in the Holocene, the last 10 or so 1,000 years, post-glacial time period. And right here it says pre-agricultural soil surface. So that black layer there is a organic rich soil layer that we find in a lot of our streams. Some places it's very pronounced, other places it's not. In this stream, in the Low Platte River, a little bigger system here, it's very well pronounced. And we're seeing here quite a bit of sediment deposited there on top of that black soil. So that serves as the marker of where the floodplain elevation would have been at the time that European Americans started to really populate this landscape. And the stuff above it is largely material from the uplands that was eroded and transported and redeposited down in the valley bottoms. In this case, 1.4 meters, so we're talking, 4 or 5 feet of material that's deposited there. So it's going to be very difficult for that river now to exceed that bank height, even during the largest of flows, and spill out onto the floodplain. So what's that mean? More of that water moves downstream, more of that sediment moves downstream, potentially creates problems further downstream. There are ways to actually date individual sediment deposits within these. In this case, this is a stream bank on the Grant River, and so here, this is I don't think that's Jim Knox there, just graduate students from years ago. But on here are dates for different layers of material within that stream bank. So if you clear off that stream bank, some of you may have seen this before, or if you've seen a recently collapsed bank, sometimes you'll see this banding in there, lighter and darker colors. It takes time for a soil to develop. So if you have a longer period of time where there hasn't been floods occurring, then you'll get a darker color. If you have a flood deposit, it tends to be a lighter color associated with it. So it creates that banding. In this case, this was Grant County. There was lead mining that was going on there as well. And so what we have here is lead concentrations going down through the core. And where you see peaks in lead concentrations, those are associated with floods that were taking mining spoils, essentially, and transporting them, depositing them out on the floodplain. So that and some other things can be used to come up with then the points in time, which then can be used to come up with the sedimentation rates. The rate at which material is grading or building up on the floodplain. And so we see that with initial mining and then poor land management for agriculture, we see an increase in sedimentation, but then it drops off. It drops off there, and in this case, post-1950. Some of that is because the bank is just so damn high at that point, so darn high. It's gotten pretty high. But some of it is thought to be related to improvements in how we use the land. And so if we went to this site in nearby Grant County in 1950, actually I thought this was an earlier photo than 1950. I think I have a typo there. I think it's 1940. But if we went out there, we would see, these are farm fields that we have there, and there's not much tree growth there. There are gullies and fresh exposed soils that are found there, eroding. So there's potential for a lot of erosion, surface runoff, sediment transport to occur on this landscape. If we go out to that same location today, it's a vastly different landscape. And so, this is what we're used to seeing when we drive around. So we got strip cropping, contour farming, we're fencing out the cattle from the steeper slopes. And so this is helping to protect those soils and reduce the amount of erosion, which ultimately reduces the amount of downstream transport of sediment into our rivers, which maybe is leading to this reduction in sediment deposition rates on the floodplains. And so I'm sure many of you maybe have heard of Stan Trimble before. He did quite a bit of work here in the region in Coon Valley, looking at sediment and rates of sources as erosion from different sites, sinks as deposition in different areas. And so note that, so this is 1853 to 1938. Well, all I want you to think about here is the size of these arrows. They're big, meaning a lot of sediment's being moved and then deposited. Okay? If we fast forward a little closer to present, we see that they're much thinner. Right? So there's a lot less erosion occurring, and in many places a lot less deposition. Okay? And so the take home is that the things that have been done to improve how we farm the land have had a really major impact on erosion and deposition that I think has had really positive impacts on our rivers. Yeah.
I noticed that stops in 1993.
Yeah.
And then visually, to me, it looks like a lot of these contour strips are being taken out. And I know, just talking to my father, that a lot of these, you know, as machinery gets bigger. So are people measuring erosion since 1993, and has that affected it?
Yeah. You know, I went on a field trip with Trimble just a couple months ago, and he hasn't been out there in a while to do this. He retired about 10 years ago. All of his field notes are over at UWL in their archives at this point. So someone could pick those up. Part of the problem is that a lot of the markers in the field that were used to survey sites have, they're not very easily found anymore.
They wash away?
They're usually put up high enough they won't wash. They might be buried. Sometimes they wash away, sometimes they're overgrown, they're just lost. And they weren't GPSed in quite the way we would today. So it's tough to do some of that. Some of it's site access becomes more challenging. Property owner changes. And then some of it is the work he did on the rivers. You know, he made the argument that there's been enough fish structure put in place on rivers that has modified the natural processes in a significant way that has kind of altered what he was trying to do with his studies. So it's not done as much. My kid's got a question. Can't wait to hear what it is.
How much scouring action
Yeah,
is there back there? Scouring action!
I bring them on field trips with me once in a while. That term comes up periodically. What I do want to say here, note that these numbers here, I don't mean to flick you off, these numbers are the same for the amount of material coming out of the basin. And ideally we would have seen that these would decrease. And we're still seeing a lot of material coming out of the drainage basins and going into the Mississippi River. And that's a problem, and we'll maybe touch on that in a little bit here. So there's been some geomorphic change in terms of the size of the river channels, the height of the banks that have happened following land clearance. And we've also, but then there's been improvements that have been had following how we, the best management practices have been put in place on our agricultural fields. So what is the impact of that then hydrologically? And so this is a study that came out about a decade and a half, oh geez, I'm dating myself, a couple decades ago. And it's looking at, in this case, this is the Platte River, and so looking at peak discharge for each year from the 1940-ish into the 90s. And this line here is just showing us the trend, and showing us a general downward trend. We have some really big floods there, and they tend to be getting smaller, a couple big ones every once in a while. The argument is that the improvements in land management have retained more of the water on the land, promoted more infiltration, which has reduced the amount of major floods that have occurred. Well, if the floods are largely from surface runoff, and we're getting less surface runoff and more infiltration, we should expect that the groundwater contribution to the flow in our streams should be increasing. And that's what this one is showing. So these are low flows, 7-day low flows on the river, and we're seeing that the general trend has been upwards. So smaller floods, more groundwater contribution. Many different studies have shown this on streams all throughout the region, that this is occurring. The problem is this ends in 1990, and things have really been going haywire since 1990.
And farming practices have changed, and agriculture has
Right.
changed over the last 30, 40 years.
Right.
So
Yep.
this is
Less,
kind
potentially
of
less
irrelevant,
CRP. Well, not irrelevant if you take into account that we learned something, and we learned something that works.
Right.
And are we going to retain that memory of that, or are we going to
We've lost
go
it.
back to other practices potentially that were less successful? Yeah, no, I think it's a valuable point. So what's the response been then geomorphically to these channels? If we decrease, at least up to that point, decrease the size and frequency of those floods, then our rivers are potentially going to have smaller channels. And so what we're seeing is the development of these inset floodplains within or below the post-settlement or agricultural terrace, essentially what this is at this point up here, that the river is pretty much disconnected from. It's creating a new floodplain here. The problem is, as it's creating this new floodplain here, it's got steep banks that have a lot of material in them. If that bank fails, that's introducing a lot of sediment to the stream. As the river is laterally migrating, it's carving that material out and it's transporting that potentially downstream. And so, there are issues associated with this. Remember I said a couple slides earlier that this number here, representing material coming out of the Coon Creek drainage basin, hasn't really changed, even though we've done improvements in that basin. And this is part of that. The river, through the process of creating a new floodplain, it's trying to get back to a stable point. And that takes a lot of time for that to happen, and it requires a lot of zooming of material that was deposited in the past century for that to happen. And so it is pulling that stuff out, and unfortunately, we're seeing a return to higher flows again, which is increasing the rate at which some of that's happening. And sometimes that sediment's not very good stuff. In this case, this is down by Galena. I hate to leave the state of Wisconsin, at least partially, drainage basin, but this is a study that I contributed some to with Robert Pawlowski. These are mine spoils, pretty contaminated with lead and zinc. That wasn't a very efficient process of removing the lead and zinc. This is an older photo of a tailings pile. In both cases, there's a stream pretty close to those, and it's carving into it. Where does that material go? It gets into the river. Most of it gets stored locally, but a good chunk of it gets transported downstream and eventually ends up in the Mississippi River. This photo was taken as the Galena River was rising, and but it's out on the Mississippi, and we see these sediment plumes coming out there, that chocolate milk color, and that if you were to sample that sediment, it is pretty high in terms of its lead levels. If you sample the bed sediment of that channel, it's got high lead levels. If you sample the floodplain sediment, it's got high lead levels. The Corps of Engineers was creating fish habitat on the Mississippi River right near here through dredging because of all the sediment coming in. And they had to test it for lead levels, and certain parts of it were and zinc, and it was elevated. This is a site closer to La Crosse. Halfway Creek, anybody know Halfway Creek? It's a small drainage basin that dumps into Lake Onalaska, if you're familiar with Lake Onalaska. Lake Onalaska is a very well-known fishery, and it became very productive following lock and dam closure on the Mississippi River. Problem is you create a relatively still body of water that a river is dumping into with pretty high sediment load still. It's going to drop its sediment supply down into that body of water, and it filled it in very quickly, and the overwintering habitat for the fish was deteriorating very rapidly. So several $1 million was spent to come in and to dredge out channels in there. Well, we still have a lot of sediment coming into that site, so the question is, how are those dredge cuts doing? So I'm working with a couple of students, and we're doing sonar surveys in here, and we're just at the point now where we can do a quantitative analysis to say how much fill has come in. The good thing is it hasn't been more than a meter, which is 3 feet or so, it's still a lot. But the good thing is they actually dredged a very, very deep hole where the Halfway Creek comes in intentionally for that sediment load to mainly fall out of suspension into that hole rather than coming out here and filling in there. And we're seeing 3-4 meters of deposition in that hole, so there's a lot of sediment coming in there. In addition to that, to this point, there's been changes in more recent years. Sorry, it's so loud, but changes in more recent years to some of the amount of conservation reserve property land, more marginal lands potentially putting back into rotation. And we're also seeing an increase in frequency of really, really high intensity rainfalls. And we've experienced this almost, it seems like every year, sometimes consecutive years in the same basin. So when you dump 6 to 8 inches of rain on the landscape in a matter of several hours, or less than a day, even under best management practices, the ground can't really soak that up. Maybe under prairie conditions, but it can't really soak that up, and so we get a lot of runoff that occurs, we get a lot of erosion that happens, we get a lot of channel erosion. This is Norska down. We can see coarse sediment load introduced, but also a lot of bank erosion that's happening. And so this was the bridge in going into Coon Valley, and you can see that water looks like chocolate milk. And that's actually the trout fest sign there for that building that got stuck up against the deck of the bridge. That year's trout fest was canceled, I believe. So we're not in the clear at this point. A lot of those problems that we kind of worked through and made improvements on are coming back in some ways. And so we're still experiencing some of those things, and we can, I think, put into practice some of these things that we've learned over the years. And there is a lot of stuff that's going on to try to continue to rehabilitate or restore our streams. Sometimes it involves stabilizing the river so it has a harder time eroding into its banks. It might include building fences to keep cattle out, building stream crossings for cattle, make sure your culverts are large enough for the water to pass through. This is an interesting project on the Pectonica River. So there was that black layer of topsoil with the post-settlement sediment on top of it. Well, you can drill down into that and figure out how far you got to go to get to that black topsoil that represents the pre-settlement soil. You can build that out into a map, hand that off to a person operating an excavator, and say, dig down to that level, and you can reestablish that pre-settlement elevation. But if you got a lot of sediment still coming through the system, there's potential that it'll fill back in. Though that doesn't seem to be happening as quickly. You can regrade the streams. There's all kinds of stuff that you can do to try to improve these things.
Do you have a feeling about the efficacy of bank armoring and the riprap along those banks and on a naturally meandering stream? Is it making sense, or is it vary by site? Or
I think it can be very effective if you use the right size materials for the size flows that are likely to potentially come in there. Ecologically, it's generally not considered to be the greatest thing. But if you're trying to, if your river is maybe on impaired waterways list because of phosphorus loading, a lot of that phosphorus might be coming from what we call those legacy sediments within the stream bank. Then it might make sense that you armor that bank because you're trying to control for phosphorus coming out. But there are other sacrifices you're making for that to happen. The river is going to try to get sediment from somewhere. It might go downstream and expend that excess energy downstream to pick up the sediment that it's looking for.